Hello, welcome back to Introduction to Mathematical Statistics. So in our previous video, we checked conditional probability, and we have the definitions to be probability of C1 given C2 to be equals to probability of C1 intersection C2 over probability of C2, and then from here we can derive our multiplication rule by cross multiply, and we have probability of C1 intersection C2 equals to probability of C2 times probability of C1 given C2. So if we have more than this, if we have more than two sets, then we can also derive the multiplication rule for that. So with that, we have what it we define the law of total probability, which we actually use to be able to define the Bayes theorem. We have the total probability so if we have C1, we have let C1 dot Cn be partition of our of our sample space, fancy C or call it C. Then for any event C, we have the probability of C to be equal to probability of C1 times probability of C given C1 plus probability of C2 times probability of C given C2 plus plus probability of Cn times probability of C given Cn. So then we now define our Bayes formula. Probability of Ci given C is equal to probability of Ci times probability of C given Ci over probability of C1 times probability of C given C1 plus plus probability of Cn times probability of C given Cn. Alright, and then we check some examples for better understanding of that. So today we are going to do independence. So let's check the definitions for independence. So definition: two events C1, C2 are called independent if probability of C2 given C1 by the definition should be equal to probability of C2 intersection C1 over probability of C1, but these are independent if this is equal to probability of C2. In other words, probability of C2 times probability of C1 over probability of C1, and this cancel this, and that is equal to probability of C2. So this is the basic definition. So if this condition holds, then you see that our events are independent. Okay, so in other words, we can define it as if C1 comma C2 are independent, then probability of C1 intersection C2 is equal to probability of C1 times probability of C2. Okay. So then you can also try to prove this theorem. If C1 and C2 are independent, then the following pairs are also independent. That is C2 and C1 complement, and C2, C1 complement, and C2, and then C1 and C2 complement, and C1 complement, and C2 complement. And that is probability of C1, C2 intersection C1 is equal to probability of C2 times probability of C1, and this is probability of C1 complement intersection C2 equals to probability of C1 complement times probability of C2. This implies probability of C1 intersection C2 complement equals to probability of C1 times probability of C2 complement, and this also implies probability of C1 complement intersection probability of C2 complement equals to probability of C1 complement times probability of C2 complement. Alright, so let's check some example on this. Look at this beautiful example. So a red die and a white die are cast in such a way that the number of spots on the two sides that are up are independent events. Okay, we have if C1 represents a 4 on the red die and C2 represents a 3 on the white die, with an equally likely assumption for each side, you have to find the probability of the other pair. Red equals to 4, white equals to 3. So probability of red equals to 4, common white equals to 3. So that is equals to probability of red equals to 4 and white equals to 3. And that's equals to probability of red equals to 4 times probability of white equals to 3. And that's equals to 1/6, because 4 only appear once in a die, and we have 6-sided dice, and then for white also 3 appear once, so we have 1/6 times 1/6, which equals to 1/36. So that is for question number 1. Question number 2, that the sum of the up spot of the two dice equals 7. So for us to check this, you see we have the probability that the sum of the up spot of the two dice equals 7. And we are going to list the possible outcome for that. You see we are going to have 1,6, and 6,1, 5,2, and then 2,5, 4,3, and 3, 4. What else? That's all. Okay, and then if we take the probability of these since they are independent, then we have, for this we have 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6 plus 5 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6, and that's equals to 1, 2, 3, 4, 5, 6, that's 6 over 36, and this equals to 1 over 6. Alright, so let's now define mutually independent. Definition: three events C1, C2 and C3 are called mutually independent if they are both piecewise independent and three-wise independent. So what do you mean by that? What means the probability of C1 intersection C2 is equal to probability of C1 times probability of C2. Okay, and then probability of C1 intersection C3 is the probability of C1 intersection probability of C3, probability of C2 intersection C3 equals the probability of C1, so it's C2 intersection probability of C3. So probability of C1 intersection C2 intersection C3 equals the probability of C1 C2 times probability of C3. Okay. Then we can also define that for finite set of events. Let's see a finite set of events C1 dot Cn are mutually independent if and only if every collection of k equals to 2, 3 dot n of these events are independent. Okay, such as when the event C1 complement and C2 union C3 complement union C4 are independent, and then the event C1 union C2 C3 complement and then C4 intersection C5 complement are mutually independent. So then we can continue to perform a sequence of random experiments in such a way that the events associated with one of them are independent of the other event. And then for convenience, we just refer to this event as independent experiment. Okay. So let's check some example. So if your coin is flipped independently several times, let the event Ci represent a head on the height toes. Thus Ci complement represents a tail. So you have to find the probability 1 of an order sequence like H, and 2 you have to observing the first head on the third flip, and then getting at least one head on 4 flips. So let's check the solution of this. Solution. So for the first one, we have H, T, H, and then we have the event I represent the head on the eye toes, and Ci complement represents T. So we have to find the probability. So that means the probability of C1 intersection C2 intersection C3 complement intersection C4, because our complement represents 10 and our Ci represents 8. So this is probability of C1 times probability of C2 times probability of C3 complement times probability of C4, and this all equals to 1 over 2, 1 over 2, 1 over 2, 1 over 2, that's 1 over 16. Okay. So the next question is the probability of observing the first head on the third flip. The first head on the third flip, that means that we have 10, 8, and that's probability of C1 complement intersection C2 complement intersection 8, and that's equals to probability of C1 complement times probability of C2 complement times probability of C3, and that is half raised to power 3, and that is equals to 1 over 8. And next, thus we have to find the probability of getting at least one head on 4 flips. One head on 4 flips. At least one head on 4 flips. So you can just find the probability of no heads on the 4 flips, and then we'll not take the intersection. Okay, so probability of at least one head on 4 flips equals to 1 minus probability of no heads on the 4 flips. So no 8 on the fourth place means that we already have 10, 10, 10, 10. And that equals to 1 minus probability of t times probability of t times probability of t, probability of t. And actually this, we should represent this as C1 complement intersection C2 complement intersection C3 complement intersection C4 complement. And by that we have 1 minus P C1 complement times PC2 complement times PC3 complement times PC4 complement, and that is equals to 1 minus 1 over 36 over 16, and that is equals to 15 over 16. Okay, so here we stop, and then in the next video we check some exercises related to under this videos we have checked so far. That's conditional probability and the independence probability. So hope to see you in the next video. Thank you.